You know when you see one of those super complicated polynomial equations? The ones with a ton of different terms and powers, and you just wonder what on earth does that graph even do? Like way out on the far left and the far right. Well, there's actually a really powerful tool that lets you predict that endgame without ever having to touch a calculator. It's called the leading coefficient test, and today we're going to learn how to predict any graph's ultimate fate.
So that's the big question, right? How can we possibly know where a graph is headed just by a quick glance at its equation? It might seem like some kind of algebra magic, but believe me, it's not. It's actually a totally predictable outcome based on a couple of very, very simple clues.
All right, so here's the game plan. We're going to break it all down into 5 simple parts. First, we'll talk about what predicting the endgame really means. Then we'll unlock the math codebook that makes this whole thing work. After that, we'll run through some examples, cover some pro tips so you don't fall into common traps, and finally, we'll ask a new question about everything else that happens on the graph.
Okay, let's dive into Section 1, predicting the endgame. The whole goal here is to upgrade our vocabulary, to move from just saying things in plain English to using the precise and, honestly, more powerful language of math.
Think of this as a direct translation. We might say something casual like, the right side of the graph goes up. Math just has a more efficient way of saying that. Now, this notation can look a little scary at first, but it's really just shorthand. Here's all it means. X is your horizontal direction, left and right. F of x is your vertical direction, up and down. So when it says x approaches infinity, that's just a fancy way of saying as the graph goes way, way out to the right. Simple, right?
Now for our second section, let's see how this all comes together with what I like to call the math codebook. Seriously, think of this as the secret decoder ring for every single polynomial graph you will ever see. It's the one tool you need to solve the entire puzzle.
And here it is. This little grid is the heart of the whole thing. All you need are 2 little pieces of info from your polynomial. Its degree, that's just the highest exponent you see, and its leading coefficient, which is the number attached to that biggest term. That's it. Those 2 facts lock you into one of these 4 boxes, and that box tells you exactly where the graph's arms are going to point.
Okay, Section 3, Examples in Action. Enough with the theory, let's get our hands dirty and put this new decoder ring to work on some real functions.
Let's kick things off with a nice, clear example. F of x equals negative 2x to the 4th plus x. Step 1, we find our code. The highest power, the degree, is 4. That's an even number. The coefficient on that term is negative 2. That's negative. So step 2, we look it up on our grid. Even degree, negative sign, and boom. That means our graph falls on the left and falls on the right. Step 3 is just writing that out formally with our cool new limit notation.
See? Just like the codebook told us. Even degree, negative coefficient, and the result is down, down. It really is as simple as that.
All right, let's flip this around. Let's try to reverse engineer it. What if you see a graph that goes down on the left and up on the right? What does that tell us about its equation? Well, step 1 is just to describe what we see. Down on the left, up on the right. Step 2, we play detective and find that pattern in our codebook. Which box matches down/up? That tells us the function has to have an odd degree and a positive leading coefficient.
And there it is, right on the grid. That down-up behavior locks us into the odd and positive category. It's an awesome tool because it works both ways.
Okay, for our last example, things can sometimes look a little tricky. When a polynomial is all factored out like this, you can't just spot the leading term right away. But here's the secret. You only need to multiply the terms with the highest power of x from each piece. Just the biggest parts. Ignore everything else.
So for a function like this one, h of x equals negative 4x times 2 minus x cubed, we just multiply the negative 4x by the negative x cubed. A negative times a negative is a positive, so that gives us our leading term, positive 4x to the 4th. And from there, it's the same easy process. The degree is 4, which is even. The leading coefficient is plus 4, which is positive. We look it up, and the pattern is up by up. Both arms of the graph are going to point towards positive infinity. Let's just check our grid one last time. Even degree, positive coefficient, lands us right in the up u box. See, the code always works.
All right, on to Section 4, Pro Tips and Pitfalls. Now that we've got the technique down, let's make sure we really master the details and, more importantly, avoid some really common tripwires.
Okay, this is probably the #1 mistake people make, mixing up the variables. Just burn this into your brain.
x is about going left or right on the graph, f of x is about going up or down. Keep those two straight and you'll be golden.
And here's another thing, a bit more of a concept pitfall. That little arrow, it doesn't mean equals, it means approaches. You see, infinity isn't a place you can actually get to, it's a direction you travel in forever. The arrow is describing the journey, not the final destination.
So you might be thinking, okay, cool, but why does this endgame stuff actually matter? Well, in fields like algorithmic trading, it's everything. A computer model for a stock can have all sorts of little bumps and wiggles in the short term, but the leading coefficient test, it predicts the ultimate long-term trend. If the end behavior goes to negative infinity, that model is basically screaming that the company is headed for failure, no matter how good things might look this week.
And that brings us to our final section. What happens in between? We have totally cracked the code on where graph starts and where it ends, but what about the journey itself?
So if you take away just one thing from all of this, let it be this. A polynomial's end behavior is never, ever random. It is always controlled by just two things, and two things only: whether the degree is even or odd, and whether the leading coefficient is positive or negative. That's the whole story.
Which, of course, leaves us with one last, really interesting question. We know where the journey begins, and we know where it ends. But what determines all the cool twists and turns, all the peaks and valleys that the graph takes along the way? Well, that's a story for another time.